Hello guys and welcome back to the course. In today's lesson we are going to learn how to compute the length of a curve in a given interval. Let us consider a continuous function f of x in an interval a, b. Our goal is to measure the length of the curve from the point a, f of a, to b, f of b. The way that we are going to measure the length of that curve from the point a, f of a, until the point b, f of b, will be by taking some points in the x-axis in the interval a, b. Let's say a being the initial point, x1, x2, so on until xn, the final point being equal to b. And we will consider the points a, f of a, x1, f of x1, so on until the point xn, f of xn. And we will bind those points by line segments, and we will compute the distance from one point to the next one. And if we do that and we add all of those lengths, all of those distances, we will get a very good approximation of the length of the curve in the interval a, b. Now, let us consider two random points, p sub I minus 1 and p sub I, being p sub I minus 1 the point x sub I minus 1 f of x sub I minus 1, and the point p sub I will be x sub I f of x sub I. Now, we know that for getting the distance from p sub I minus 1 to p sub I, we need the Euclidean measurement, meaning the distance from 2 points being calculated using the square root of x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared. If we notice in the last expression, we have that the expression x sub I minus x sub I minus 1 will be equal to some delta x, whereas by using the mean value theorem for derivatives, f of x sub I minus f of x sub I minus 1 is equal to f prime of c sub I times delta x, where c sub I is between x sub I minus 1 and x sub I. Therefore, we can rewrite the expression for computing the distance from p sub I minus 1 to p sub I, which in this case will be equal to the square root of delta x squared plus f prime of c sub I times delta x squared, which can be rewritten as the square root of 1 plus f prime of c sub I squared times delta x. And as we mentioned before, if we add all of the distances from one point to the other, we get a very good approximation of the length of the entire curve from A to B. But this approximation can be improved if we take the limit. And if we do so, when we take the limit of a sum, we are dealing with the integral definition. Thus, for computing the length of the entire curve from the point A, f of a, to the point B, f of b, we need to do the integral from a to b of the square root of 1 plus f prime of x squared dx. Let us consider the function y equals x to the 3/2, where x is in the interval from 0 to 5. Now, we want to compute the length of the curve described by this function in the interval from 0 to 5. Now, first of all, we need to compute the derivative of this function, which is 3/2 times x to a half. And y prime squared is equal to 9/4 times x. Thus, the length of the curve from 0 to 5 will be given by the integral from 0 to 5 of the square root of 1 plus y prime squared dx. And by doing the substitution, we will have the integral from 0 to 5 of the square root of 1 plus 9/4x dx, which can be rewritten as a half times the integral from 0 to 5 of the square root of 4 plus 9x dx. We have to apply substitution for solving this integral, and if we do so, and we solve the integral, we have as a result 1/27 times 4 plus 9x to the power of 3/2, which we have to evaluate from 0 to 5. And if we do so, we get 335 divided by 27. And that was how to get the length of a curve from a given point to another. Now it's time for you to practice by solving the following problems. So, as usual, see you in the next video.